In this video, we work another logarithmic differentiation problem. We're given h of x equals this. So we've got a product in the numerator. If we were to take the derivative of that product, we would have to use the product rule with the chain rule. And we've got a function raised to a power in the denominator. So if we take the derivative of that, we'll have to use the chain rule. So if we just use basic differentiation rules to compute this without taking the logarithm first, and we'd have to use the quotient rule, and then when we take the derivative of the top function, we'd have to use the product rule with the quotient, or the product rule with the chain rule. And we take the derivative of the denominator, we'd have to use the chain rule. So it gets relatively involved. But if we use logarithmic differentiation, it's actually relatively simple. And so the whole idea behind logarithmic differentiation is that if we take the log of both sides and then use log properties to rewrite this expression on the right-hand side, we can make this function much simpler to differentiate. And then we can differentiate implicitly to get h prime by itself. And so that's the plan. And then here are the three log properties we use. The natural log of a times b is natural log of the first factor plus natural log of the second factor. And we also know that natural log of a divided by b is natural log of the numerator minus natural log of the denominator. And if we have natural log of something raised to a power, we can bring that power out front. So with that in mind, and this property of rational exponents, the nth root of x to the m is x to the m divided by n. So that index of the radical goes in the denominator, and we change to a rational exponent. I can compute h prime by first rewriting this. That square root I'm going to rewrite as a 1/2 power on that function 3x minus 2. So this x squared times 3x minus 2 to the 1/2, all divided by x plus 1 squared. And now we can take the logarithm of both sides and then simplify this side using these log properties. So let's do that. We'll have the natural log of h of x equals the natural log of this quotient on the left. So sorry, the other left, my right. And the log of a quotient is log of the numerator minus log of the denominator. So we could have stand back, you sort of look at it and squint, and you say, that's a quotient in there. So we take the log of the numerator and we subtract the log of the denominator. And then to simplify this, we notice that we've got a product. This would be our A, and this is our B. The log of a product is the log of A, the log of that first factor, plus log of the second factor. And now I see I've got a function raised to a power inside each of these. So in each case, I can bring that power out front. We're going to have 2 natural log of x plus 1/2 natural log of the quantity 3x minus 2 minus 2 times natural log of x plus 1. So the natural log of h of x is equal to this, but we might have some domain issues. This might not have the same domain as the original function here. So we should really look at the domain of that original function. The domain of h includes all x values that do not cause division by 0, even roots of negative numbers, or logarithms of negative numbers or 0. So the domain of h actually is all real x values, such that denominator is non-zero. So the denominator is equal to 0 and x equals a -1. So x cannot be -1. And we need the expression under a radical whenever we have an even root to be greater than or equal to 0. So we need 3x minus 2 to be greater than or equal to 0. So if we rearrange this, we have 3x is greater than or equal to 2, which implies x is not equal to -1 and x is greater than or equal to 2/3. So the domain of h starts at 2/3 and goes to infinity. We should also rule out -1, but -1 is not on that interval, so that's not our concern. That's the domain of the original function, and we want this function to be defined on that interval as well. And it is. This is defined for all positive x values, which is a subset of that domain. This is defined for x greater than 2/3, strictly greater than, so we would have to rule out that 2/3. And then this is defined for x greater than -1, which is on our interval. So the original function h is defined on this interval, but this natural log of h has a problem at that 2/3. I'm not sure that that concerns us when we're computing the derivative though. Okay, so this is the domain of h. The domain of the log of h is all of these points except for that 2/3 at the beginning. And now we want to compute h prime by taking the derivative of both sides with respect to x. So the derivative of log of a function is 1 divided by that function by the chain rule times the derivative of the inside. You can write that as h prime of x, or you can write it as dh dx. I'll use Leibniz notation. And that equals the derivative of this piece. So that's relatively easy. The derivative of 2 times natural log of x is 2 times 1 over x. The derivative of 1/2 times that natural log of a function is 1/2 times 1 over the function. That function is 3x minus 2 times the derivative of 3x minus 2, which is just a 3. So I'll put that in the numerator. And we'll subtract 2. And then multiply by the derivative of natural log of a function. So we have 1 over the function again. Times the derivative of the inside, and the derivative of x plus 1 is just 1. And then if we simplify, this is 2 divided by x plus 3 divided by 2 times the quantity 3x minus 2. Oops. Minus 2 divided by x plus 1. And so dh dx is actually this function times h of x. Now we want a function of x only, so we replace h of x with what it was. It was this expression. Now we could simplify this if we wanted to, but we do not have to. We can leave this alone. H of x is x squared times 3x minus 2 to the 1/2, all divided by x plus 1 squared. And that's our derivative. So it's relatively easy to do, to use logarithmic differentiation to find the derivative. Now remember, this is going to give you a slope at any x value in the domain, except for those x values for which this is undefined. So we're going to get the slope at every point in the domain except for 2/3. This equation would give us the slope. At x equals 2/3, we'd be dividing by 0 here. So that derivative might be undefined. We would have to evaluate it and simplify to see. It's possible that the function has an undefined slope there, or a vertical tangent line at that location. But it might be helpful to actually look at it. Or this derivative might exist in a limiting sense. Like we might actually approach a limit as x approaches 2/3 from the right. So now if we want to, we can find the equation of the tangent line at any point x naught, excuse me. It's going to be y equals h evaluated at x naught plus this dh dx, or h prime at x naught, times x minus x naught. So that's change in y over change in x times a change in x. That's going to give us a change in y. We add the original y value and we get the y value on the tangent line. Let's say for any x naught in 2/3 to infinity. And we can graph those, we can graph that tangent line. We can graph the derivative. We can graph the original function. We'll do all of that on Desmos. I do want to outline what we've done here for as far as logarithmic differentiation is concerned. If you have a product or a quotient or something involving products and quotients and powers, often we would use logarithmic differentiation. So we'll say, use this when the function that you're interested in is a product, a quotient, a power, or a combination of those. And then how do we do it? We take the natural log of both sides. Or you can use log base 10. I have a tendency to use natural log. Then we simplify the right-hand side using log properties. We did that to here. We didn't have to find the domain, but I like to find the domain so that I know which x naught and I can substitute into this function. And we also know from our discussion that the domain of h prime might be 2/3 to infinity. Because if I simplify this times this, I end up with a 3x minus 2 to the 1/2 in the denominator. So that will be undefined when x equals 2/3. We found the domain of h, and we inferred the domain of h prime. And then we computed an equation involving dh dx by differentiating implicitly on both sides with respect to x. Given that h is a function of x. And then at the end, you're going to have this 1/h times the h dx equals a function of x. Multiply both sides by h and then substitute. H equals the original function. I guess what I should say is substitute the original function for h. And then that gives you your derivative. That's your final answer. And then we have the equation of the tangent line. All right, so let's look at this on Desmos, see what our graph looks like. So we'll look at the graph of the derivative as well. And then we will plot some tangent lines. So this is our logarithmic differentiation page. There's something about this that's really bothering me. It looks like the y-axis or the x-axis is sort of decreasing as you go from left to right. But I think it's just, I think it might be an optical illusion. Here I've graphed h of x. We said that the domain was 2/3 to infinity, and we see that that's true. I plotted that point of intersection when x equals 2/3, h equals 0. And we used logarithmic differentiation. So first we took the log of h on both sides, and then we used our log properties. So this product, x squared times 3x minus 2 to the 1/2. When we took the log of that, it became 2 times natural log of x plus 1/2 natural log of 3x minus 2. And since we had an x plus 1 squared in the denominator, that became a -2 times natural log of x plus 1. Because the log of a quotient is log of the numerator minus log of the denominator. We brought the power out front for that x plus 1 quantity squared. So it became 2 times the natural log of x plus 1. And this natural log of a product in the numerator became a natural log of x squared plus natural log of 3x minus 2 to the 1/2. And then we brought the 1/2 out front and the 2 out front. So that is our natural log of h. Then h prime is the derivative of this right-hand side, just using logarithmic differentiation. So we get that constant times 1 over the function inside times the derivative of the inside in each case. And then that equals that 1/h times h prime. So we multiply both sides by h, and then we remember what is h in terms of x? Well, it was that original function x squared times the square root of 3x minus 2 divided by x plus 1 quantity squared. So we end up with this function of x. And we see it kind of has this weird corner here. It looks like the function has a vertical asymptote at x equals 2/3. So we can see that graph is getting very, very close. Oops. To the line x equals 2/3. It's almost indistinguishable. And then we said this is the equation of the tangent line. At any x naught in the domain, and the domain is 2/3 to infinity. So I want to plot the point x naught h of x naught. And I'm also interested in the slope of that tangent line. So I want to plot x naught h prime at x naught. So for this particular tangent line, the blue tangent line that passes through the graph at x equals 9.3, y equals 4.14898 at that x y pair, the slope of that tangent line is this 0.32691. So the green values are the values on the green graph are giving us our slope. And then we can actually see that slope visually if we look at the tangent line itself. Well, we can change x naught if we want to. I let x naught go from 2/3 to 15. And then we can see the tangents at each of those points. So the slope at 2/3 turns out to be about 2.44316. But then as we get away from that 2/3, the graph quickly flattens out. And the slope becomes very small very quickly. And so that's it. That's what our graph looks like. If we want, we could keep going. This really depends on what our range of x values are. We could make the upper bound 30 if we wanted to. Then our tangent line would go all the way up here. You can pick any interval you want. I think I might just let y go from -5 to 10. So that we're zooming in a lot. And then let's let the x values go from, well, -2.5 to 30 is fine. Well, maybe we'll just go for -2.5 to 20. If we only go to 20 on the screen, we shall just go to 20 there. And if we want, we can play it. Yeah, slow that speed down a little bit. We see that that slope is decreasing. It's always a positive slope. If we want the value of that positive slope, we look at the green, the y value on the graph of the derivative function. They say, what is the slope at this location at x equals 12.86? Well, the slope is 0.27194. And of course, it's maybe not obvious that that's the slope, but if we did this zoom square thing, so everything was to scale, then it might be a little bit more obvious. That bottom line does not look like it's, it looks like it's decreasing as you go from left to right. But I think it's misleading because of the shape of that derivative graph. It has that weird corner on it. Okay, so that's our implicit differentiation example. I think I might add this to the videos from chapter 2. Or I said implicit differentiation, I meant logarithmic differentiation. We discussed logarithmic differentiation in chapter 2 in video 12 or 2.12.6. I might add this video right after that one on the Calculus 1 playlist. But then I think for right now, we're going to be done with our logarithmic functions, or derivatives of logarithmic functions. We did a lot of different examples involving logarithmic functions. And in the next set of videos, we'll look at some, I think, differentiation involving exponential functions. Might be wrong. I don't remember what 5.1 is, but it's something like that. We're continuing to look through the problems in chapter 5, which involve applying all of those concepts and techniques that we learned earlier in the semester to transcendental functions. So logarithmic functions, exponential functions, inverse trig functions. And I think that's pretty much it. So that's the plan. I'll see you next time.